the idea is to make all the lectures independent from each other. The concepts are common. So, so basically this talk will be some exposition of few things in my last article. And also there is a book which I'm writing, but the basic content you need from here. Here you do, this is the article is called elliptic modular formulations 2. So, but the idea is that I will try to talk today about the Hodge Loci aspect, which is the main. Okay, so let's first introduce upper half plane as usual. Zero. And there is another useful notation, H is rel, S star, which is H together with rational number and also infinity. So maybe what I'm going to do, first to introduce the modular curve, then D will be integer, and then I will need gamma not T. Sometimes people call it N also, but it doesn't matter. This gamma not T is matrices A1, A2, A3, A4, S2Z, such that determinant is 1 and then A3 convert to 0 modulo D. I'm sure you have seen already this group. And what is the complex version of the modular curve that I'm talking about is X not D, which is just gamma not D. So the action will be the usual Frobenius one. And maybe, so let me just make a topological picture. At the end, it is well known that this is a kind of compact Riemann surface. The reason why we put these rational numbers, they will use to compactify. It's a compact Riemann surfaces. The one, this will be corresponding to, let's say, the action of gamma 0 D. Let's call this one Q star. Okay, Q star. So this will be a finite number. This means that we can add this point to the action of gamma on H and compactify it. So we will have a compact Riemann surface. You can count the number of cos. You can calculate the genus. Something. Okay. So this is the modular curve that we are needing. And maybe I will need isolation series. So I am going to announce what actually we are going to get, but the idea is that to put all these things in the Hodge Loci context, maybe K Z 2K minus 1 and 3, 2, 5 and tau, and then here it is n equals to 1 infinity, and then I have forgotten 4K BK. These are the Bernoulli numbers. integers. This is sigma I n is just the sum r to the I r divided d. Oh, sorry. I will use n. So the sum of divisor to the I. Okay, so this one I needed. And for some geometric reason, I need a multiple of these isolation series. So at the end of the day, these are holomorphic functions on the upper half plane. And I will need just for k equal to 1, 2, 3. And okay, so I will need what I am going to need. I will need this notation because of this geometric converter. It is just a multiple of e2i and k, and then a1, a2, a3 is just 2 pi I, 12, 12, 2 pi I, 12, 2, 8, 12, 3. Anyway, okay. So these are the ingredients that I need to at least justify this new model, and then the rest of the talk will be justified from where this model comes. Actually, I didn't find this model nowhere, so let's do it. So I will take this projective space with weights 2, 3, 2, 3. This is the projective dimension 4. I will take coordinates here. Since one of the weights is 1, I can use this one to put 1 and take the corresponding affine chart. So I will use this notation x2, y2, x2, x3. The indices just they show the weights that they have. So I will use this affine chart. And okay, so today I'm going to talk about this map, from where it comes, and what is this map? So maybe I first write it. Tau is going to map to G1 tau minus d G1 d tau. Maybe I need to write and then I explain. And then G2 tau, G3 tau, and then G2 G2 d tau and G3 d. Okay, so for now it is a map from the upper half plane to this weighted projective space. So let's so for the first coordinate I will make this. This is isolation set E2. Just don't forget it. So I will make this combination. So if you know modular form, everything that you see here, they are modular form for gamma naught. This is isolation set. This is modular form by SL2Z. This is the modular form by SL2Z. But something which is well known, if you multiply the argument of a modular form for SL2Z with some natural number, then you will get modular form for gamma naught D. But something again which is not so much clear in the literature, and it has to do with if you are expecting modular form. G1, remember that the isolation series E2 is not a modular form. it has this functional equation with one extra piece. But the point is that if you make this kind of combination with E2, then that term will be cancelled, and you will really get modular form for common advantage. Do you know this one? So exercise. Take you know the functional equation of G1, the E2. It was something like maybe okay. It was something like G1 A tau plus B tau plus E, and then C tau plus E. Okay, I'm writing the format of ABC. Sometimes I will write this ABCD, but I write in this one because this D will be confused with this D. That's right. But at the end of the day, so this guy is, if G1 is a modular form, then it must satisfy this functional equation, but it doesn't satisfy. There is some strange term like this. But the point is that if you apply the elements of gamma naught for this one, this term will be cancelled, and you really will get the. So this you will get the modular form for gamma naught. Okay. And also the same exercise, any modular form for SL2C, if you multiply its argument by natural number D, then that guy will be modular form for gamma. Okay. So this map will be actually holomorphic, and the image that's denoted by polynomials with Q coefficient. Even so that our description is transcendental, but this guy is algebraic curve. If I don't care about its field of definition, there is this Chow theorem. Any compact subvariety of a projective variety, every compact analytic holomorphic subvariety of projective variety is algebraic. So at the end, the image must be algebraic, but the claim is also that it is defined. It's a curve defined over Q and so on.
Why is it clear that the image is algebraic without?
No, for example, one way is this: if the image is not a point, this one can be easily checked by Chow theorem. What is the Chow theorem?
Chow theorem means so that
Any closed.
Any closed, but it's not closed.
Yeah, but remember that this is exterior. This thing I have made it compact.
Oh yeah. Oh, you mean compact?
It's compactified. So the idea here I am a little bit skipping the detail. The map is also holomorphic. It's going to be holomorphic at the cusp. So it is holomorphic everywhere. And okay. Anyway, something that I will not invest too much is the modular form theory aspects of whatever is going on with Hodge Loci. But okay, so maybe a kind of, no, actually it's a kind of easy proposition. So the point is that taking modular curve, I'm trying to embed it as to give an algebraic structure to modular form. Modular curve using modular form is a kind of classical. But the point is that this combination of modular forms, I'm going to tell you about how they pop up in the Hodge Loci context. And maybe I will not prove it, but that's just for the sake of completeness. Put it here. Maybe let's do it like that. Because, for example, at the end, define our Q also. It is one has to. It's not immediate. And so the point is that in this affine coordinates, I will take in the last talk there was this PCOB anomaly equation. There was a lot of vector field popping up. This has to do with actually the same, has the same nature. x2 minus x3 plus 1, 6. x2 minus y2 x2. And then I put the one x3. And write the exact expression. Then the rest you have to change the role of y to y3 with x to x3. So it will be just that x going to be changing to y and vice versa. y2 minus 6, y3 plus 1, 6, y2 minus x2, y2. Okay. Okay, maybe. And these are the only algebraic curves. In so yeah, right, and then I explain. It's 3. It's 3 to the 3. 7, 43 to the 7. And you have to. So maybe I first explain. So you have this 4-dimensional x2, x4 x space. Let's say this x2, x3, y2, y3 space, and then this vector field is easily can be seen that in this space it has no zeros, so it has solutions, and any solution of vector field might be transcendental, but at the end of the day, the only algebraic solutions of these vector fields are going to be just these things, and yeah. Okay, so the question. Okay, so let's. I don't want to invest on this chair. The idea is what I'm going to do. We have a 4-dimensional space, and I'm going to justify that these curves, algebraic curves in this 4-dimensional space, they fit into the definition of the Hodge Loci that I was telling at the beginning of my lecture notes. my lectures. And so actually these curves are the first non-trivial examples of the Hodge loci, and this is the main topic. Okay, so let's okay. So something that the last talk I did, there is this new moduli space going on. See T. Well, I did in the case of mirror quintic, but I'm going to do in the case of moduli of. So it was algebraic variety. Maybe in this case I did so what is this? X1 elliptic curve. And so for simplicity, everything over complex numbers, and then alpha 1, omega 1, at what they are in H1, they're on E, and what? And then alpha 1, let's say alpha 1. Okay, sorry, okay, I'm putting 1 because I will for them just without this one. Okay, sometimes I will use also E, but let's. So let's do alpha 1 omega and this 2 pi I integration over x alpha cup omega. So in the case of one thing that I will try to do, this concept of modular space to go even beyond Calabi-Yau, but in the case of elliptic curve case, I'm considering this kind of elliptic curve. Elliptic curve, what's the modular elliptic curve? Dimension 1, okay? But I am adding to differential form, we start with this property, and then alpha is given by and in the Hodge theoretic notation, this is the same as to saying that we have this alpha is the Hodge. There is a Hodge filtration, and it is in the F1. Okay. So, what is the dimension of this moduli? Right? Can you guess? The dimension of the x is 1. You are adding alpha and omega also. Omega lives where? But it lives in the 2 dimensions. Alpha means in 1-dimensional space. Omega lives in 2-dimensional space. So apparently there are 2 and 1 freedom. But the point is that alpha and omega are perpendicular to each other. This means that if you choose omega, and you know that alpha is in 1-dimensional subspace, then the alpha is fixed. So if you choose omega, then alpha is fixed. And then you choose omega, and I have to say that they form a basis. At the end of the day, what are you doing? Maybe I take a picture. Let's say this P1, the classical moduli space of elliptic curve. Then you have, let's say, H1 here on x over, let's say, x, if you have this, let's say, x j, let's say this is j. Then there is this 1-dimensional piece here, F1. And then you are choosing the above each point you are choosing one omega. But I have to say that this is not the total space of the complement of this guy here, because when you say moduli space, if, for example, if the elliptic curve has automorphism, there might be identification. So it's not total space. But at the end of the day, the moduli space is of dimension 3, because one dimension coming from here, two dimension coming from omega. And if you little bit work out, maybe I write it. If you do a little bit work out what you will find. So that's it. Proposition. So the good point is that you can construct a universal family. There is the first double T. Okay, I'm working over C, but actually I could work over RFP, but let's stay in the case of T1, T2, T3. The discriminator. 1, 27, T2, T3 to the 2 minus T2 to the 3. So actually your T is affine variety, and one has the universal family of elliptic curves over T. And what is the universal family? Maybe I write it. So the universal family, let's say, it is the same Barrash-Grass equation. So in any point in T, I have to specify the elliptic curve. Plus 3. So this is the universal family. I have to specify this of alpha and omega. Alpha is just the class of dxy, and omega is the class of So what this means, if you fix T1, T2, T3, this x with alpha omega will give you such an element, and any triple x alpha omega is parameterized by a unique T1, T2, T3 here, and whatever definition, even if you do the categorical definition of universal family, this means that we are in a good shape and we can construct this modular space. So, okay. Well, even these things, let's say, my lecture is in 2012, but these are in some sense easy, but I didn't find somewhere. That's where I had to write it. Okay, so anyway, for my Hodge and Noether-Lefschetz stuff, this elliptic curve is useless because, as you remember, the Hodge and Noether-Lefschetz, I have to consider even dimensional varieties and so on. And okay, let's go further. Okay. Goals. Connection. 4. Even so, I am not. Well, I don't want to go to the details of Gauss-Manning, the definition of the Gauss-Manning connection. But let's do in the period language. So this is a T in T. So when you have T in T, you have a elliptic curve xt. Okay. You can take these cycles that's denoted by delta T, and you have also differential form. This will be dx x dy. So let's say the dx delta T. Okay. So let's take this T space. In T space, I take just maybe this small neighborhood of a point. So what kind of these are the elliptic integrals, and at the end they will be holomorphic in some open set in T. If you go if you go. You can make the analytic continuation along passes. This would result in monodromy and so on. But the point is that then these dx, these integrals are holomorphic functions in what? In this T1, T2, T3. Okay. So and then when you can make differentiation, this differentiation means in T1, T2, T3. And the concept of the Gauss-Manning connection is basically that you can compute these guys in terms of, again, this one. So, I go 1, and 1, 2, 1, 2, 2. The differential of the algebraic. Differential 1 forms 15. So this is the same story of the Picard-Fuchs equation and so on, but it is saying that in a different let's say language. When you make the derivation of this elliptic integral, you can write them again the combination of the previous integrals with coefficients which are going to be differential, algebraic differential form in T. And these guys are computable, or can compute explicitly. Can be computed explicitly. And if you want a fancy language for the Gauss-Manning connection, the fancy language in some senses is this one. You have this H1, there are x t going to omega 1 t H1, there are. You have the cohomology bundle, and then you have a connection there, and then you will have this alpha omega that I have written here. Alpha omega are global sections of the cohomology bundle, which is this one. And then if this is the matrix A, then alpha omega is just this A times simply alpha omega. Okay. Question. If you, for example, take a one-parameter family, then you can use this one to compute the Picard-Fuchs equation, and so on. But okay, maybe the last thing about this one, and then go to the elliptic curve case. So to the product of the elliptic curve case. Again, another proposition. There are unique. Well, this kind of unique vector field appears already in this COB stuff. Vector fields in E, F, H, in T. So maybe, okay, I write it. It's so there are the vector field which have this special. So if you, let's call this one Gauss-Manin connection matrix. Gauss-Manin connection matrix. Then then we will have this this special feature F. Okay. H. As I said, these are all results of many computation. And 0, 0, 0. Okay. So you have a 2 by 2 matrix which is whose entries are differential forms in T, and the statement is that when you have a differential one form, you can compose it with the vector field, then you will get function. So there are unique vector fields F, such that when you compose F with the entries of A, you will get this matrix. Then another one that when you compose with the A, you will get this one. And maybe I write the equation, and as I said, this A is computable, but at the end you can compute also this all these things. Minus 1, 2, 12. Maybe if somebody remembers. Minus 6, T1, T3, 1, 2, H, minus 6, T3, T3, minus 4, T2, T2, minus 2, T1. T1 and E is just the ratio with respect to T1. Okay. And you know what are these matrices? These matrices?
SL2.
They're famous. SL2. Yeah, exactly. This is the generator, the classical generators of SL2 and the algebra. But the point is that there is we find vector fields, and it turns out that these three vector fields F, H, E, with the classical Lie bracket of vector fields will be isomorphic to SL2. And okay. As I said, this is I'm telling the summary of lecture notes about concerning elliptic. But if you want, can discuss more. For example, if you have this, you want to form this PCOV anomaly equation, then the algebraic version will be exactly using these vector fields. And something that I have to remember, after the process of going to the complex side, this T1 will be isolational series E2, this T2 will be isolational series E4, and this will be the isolational series E6, or G1, G2, G6. But this one, slowly, you have to see. Okay, something also that I have to say. I have this. G1, G2, G3. Remember that there was, I defined this holomorphic satisfied the ODE of, let's say, F. What this means, if you make the relation with respect to tau, then this will be actually the minus F. This will be, so just writing here, G1 to the minus 12, G2, if you make the relation, G2 will be this one, 4 G1, G2, minus 6 G3. This is again, this is called Hodge relation between isolation. Okay. Anyway, maybe just in more 10 minutes, I will talk about where the Hodge locus pops up, and then I still remember the definition of Hodge locus. Okay, so okay. I will take the, in order to be able to do a Hodge locus, I will take the product of two elliptic curves. Okay. T dot T. So I will take also my moduli space, parameterize. At the end of the day, this T parameterized two pairs of elliptic curves. Let's say one, let's say they call it T, and the other one S. Then this X, maybe, okay, I will get X1, alpha 1, omega 1, X2, alpha 2, omega 2. And again, okay, so I want to talk about X1. X1, this X1 times X2, and so okay, so what I need in order to introduce the Hodge locus, I need a parameter space. In this case, I will take the parameter space of two elliptic curves. For me will be T times T. I need their own homology and I need homology. So I need H2 the realm of this guy. This then you use the Kunis formula, and then you have it. But I will cut it out by some trivial bit. But at the end, let's see that this has to be the notion of the polarization. Maybe I call it P. Let's define this one, just the middle part of the in the Kunis formula. So there are two other pieces which I cut it out because one can just talk about one can do this algebraic stuff just using this one. In the same way, if I want to do the dual of this guy, so I will need a homology with z coefficient. Again, I will just use part of it, and at the end it will be just h1 xz. tensor H1 theorem X. Oh, mixing everything. So this is 4-dimensional. This is 4-dimensional. And okay, so this guy has a Hodge filtration H2 theorem x1 times x2 with this notation G downstairs. What is this? This will have Hodge filtration. Zero, F0. So remember that I choose alpha 1, omega 1 here, alpha 2, omega 2 here. But at the end of the day, the natural Hodge filtration here will be this one. This is of dimension 4. This will be generated by alpha 1 tensor alpha 2. This will be generated by alpha 1 tensor omega 2 and alpha omega 1 tensor alpha 2. One element 2, 3. So this guy will be of dimension 3, dimension 1. And okay, so if I want to repeat the definition of the Hodge cycle or not the same loci, so in this context it is just one has to make sense, but it is the integration of F2 part. The F2 part is dimension 1, F1, F2 divided by a cycle, iterate our cycle, so delta in H1 X1, right? See? So this is the definition of the Hodge cycle in this case. So integration of this 2 form after going to representing a differential 2 form over the cycle must be 0. And this is the Hodge cycle. And what is the Hodge loci? I mean, just considering all deltas in all, here I am fixing element TS will represent this T, this will be T, this will be S, and then okay, but so if my space is of dimension, my space is now dimension 6. This is dimension 3. This is not dimension 3. So this is one equation. So apparently my Hodge locus is of dimension. It's called dimension 1. It's a dimension 5. But for some reasons that it will be clear later, what I have to do, I have to make the integration of the full basis, alpha 1, omega 1, omega 2, omega 1, integration, alpha 2, then omega 1. Okay, so these 4 differential forms are now a basis of this guy, and by some reason, I will consider this loci. So I have 4. If I put this, let's say this T, this delta varies in my parameter space, I will get 4 equations in a 6-dimensional space. But it will turn out that there is some algebraic relation. There is some relation between these 4 equations. They are not independent from each other. And Maybe just let's say extended, I don't know, Hodge cycle. So this is because of this extra equation. So far, this kind of equation didn't pop up. But at the end of the day, proposition let's look at that. Let's say we have to put the V delta. So, first of all, these guys are holomorphic. So, a priori, again, it is an analytic variety because there is no. But remember that once I told about this bigger theorem, Katani, Denin, Kaplan, these are really algebraic. But in this case, it is proved this one. Is algebraic subset of T times T of the dimension 3. And maybe let's consider all possible deltas. Let me take this. Okay. Okay. So maybe well, I didn't reach to the relation with the first part of my talk. But let's say what is happening here. This Hodge locus V delta parameterizes isogenies x1 with certain So maybe, okay. So remember that the notion of Hodge cycle comes from the study of algebraic cycle. When you consider product of two elliptic curves, what is the most canonical what is the algebraic cycle that we can find there? There are elliptic for elliptic curves, sometimes you have isogeny. This is a map from x1 to x2. And once you have a isogeny graph of this f will be a curve in x1 times x2. And this graph will be a curve, and this will give element in H2, x1 times x2, z is in this part, and then you will get this Hodge cycle and so on. So the point is that these guys, they are parameterizing elliptic pairs of elliptic curve, which there is an isogeny between them. And okay, maybe the last thing maybe I write it. All these deltas of tangent to this reduction or foliation in t times t given by E1 plus E2, X1 plus X2, H1 plus H2. So remember that in each t I had E, F, H, three vector field. So I made t times t. The first t I called the corresponding EFG, E1, F1, H1, and the second one I do E2, F2, G2. So I make this this kind of sum. I have three vector fields in a six-dimensional space, and it turns out that it will give you a three-dimensional subspace of the tangent space. It turns out that it is these are closed under the bracket. So, for example, basically the concept of foliation comes from where, when you have a bunch of vector fields which they are closed under the bracket. But the first part of the that I told, at the end it is one reached to here, and from here one goes to from the sixth dimension one descends to the fourth dimension, and one get this projected space P23231, and then one lands on this modular curve. So there are a lot of things going on, but something maybe for later I don't need, maybe this basic example that in t times t I have very special loci called Hodge locus, and the Hodge locus originally was just in this case was just this equation, but since I have increased my modular space from 2 dimension and come to the 6th dimension, I can have a freedom of putting other integrals also in a special way that I want. In the next lecture, it will be clear why this combination happens. But and the idea is that this kind of loci at the end will take us to the theory of polymorphic foliation. Yeah. Okay. Any questions?
At the beginning, you mentioned the modular curves related to this Hodge cycle.
So if you want to see the modular, so the modular curve this is modular. I want to write modular of x1. 2 elliptic curves with an isogeny and if I am isogeny degree f d. So any at the end of the day, okay, degree of d, maybe that's me, and maybe I have to be a little bit careful. But let's gain in this case. There are some solutions going on, but I think that it will be a crack. In this one, I'm sure. So the point is that this modular curve parameterized, it's the moduli space itself. Okay, without compactification, you have to take the cusp away. But this is the moduli of 2 elliptic curve with an isogeny, or any isogeny is determined by its kernel. So in some sense, they're the same as x1 and torsion subgroup X1 C torsion subgroup of order E. So this is the Hodge loci also parameterize the isogeny. So there are a lot of translations going on, but in order to relate to the modular curve, you have to know this presentation of the modular curve. And maybe graph of Isaac. But this kind of phenomena for Calabi-Yau varieties becomes difficult to differentiate. If you would have this Calabi-Yau threefold, can you say that in the same modular space of the Calabi-Yau threefold, there is another Calabi-Yau threefold always, but when I make a product, there is a kind of algebraic cycle of dimension 3 inside. This kind of things all becomes for example, this has to do. I want to look for Hodge cycles in the product of two Calabi-Yau varieties. So if you take Calabi-Yau threefold, then Calabi-Yau threefold times Calabi-Yau threefold is a 6-dimensional. Can you give me some non-trivial Hodge cycle, algebraic cycle, whatever in this the product? Maybe let me. Maybe something that we can do it if which, for example, in which direction you want to hear more stuff. For example, I think the point that I think if this the elliptical case you were not familiar, or because this is also a kind of this three-dimensional modular space, a kind of new. But the point is that in T itself there is no the notion of locus. Or something also that I think it would be interesting. The same is true in the case of K2 surfaces. Anyway, it's finished, huh? Finished.
Why is it suddenly from one curve to the other, not the other way? So
No, there is only dual isogeny.
You're picking a delta.
Yeah, this is
Okay.
the point that this
Yeah,
delta
it's short.
is the homology class of the graph of the isogeny
I see.
up to some part of the homology that I have cut it out.
Right.
But at the end, this delta is this. Maybe something that might be useful to write it down. Okay, something. At the end of the day, this equation, when for example x1, let's go to the holomorphic context. Again, there is some translation going on. This equation will be translated on the Mobius transformation. Tau 2 is A tau plus B, C tau plus D. Or maybe I have to take A1, A2, A3, A4, and you can this A1, A2, A3, A4 has to do with the coefficients of delta when you write in the places, but this A1, A2, A3, A4. This determinant is going to be D, and everything is in Z. This equation will be translated and this one, and isogen in the complex context it is like this. For example, when maybe the simplest one that I can take, for example, when tau2 is d tau prime. Remember that in the first part I was making the multiplication of the tau with d. This is again maybe up to SL2Z action. Any such equation you can write in this format. Tau2 equals to d tau 10. And then what is the isogeny here? Isogeny here is say maybe if I don't make x1. So which lattice is inside the other one? Tau2 is inside this one. It's in this lattice. So this means that I have a map from x2 to x1. This is induced by identity. Identity from here to here. It will give me the map because tau2 is d1. This means that the tau2, and when you go there, it's also there. And this is the isogeny in the complex context. Its kernel will be you can compute it and so on. So one of the very simple operations in modular form, multiplying with the argument with t. And this has to do with the isogeny of corresponding electrical.